To predict the density of a 3D printed part, it was first necessary to create our control group. To do this, we used 5 different bricks that we 3D printed that were equal volume but varying density. As you can see on the screen, these were our 5 control groups. We hit these control groups with a pendulum and recorded the resulting acceleration with Vernier motion analysis and an ultrasonic sensor. Although this setup would have been most likely more accurate with an accelerometer, an ultrasonic sensor worked for us because between the tests it was proportional to one another. On the screen, I am tapping and switching out the bricks with my finger to represent the process we took while hitting these with a pendulum. We then correlated our control values, mapping the x values for acceleration and the y values for density. We measured the acceleration of our experimental brick to try and see if we could predict the density of that brick using our 5 control bricks. We measured the initial peak acceleration of the acceleration graph and then compared this to the slope of the velocity graph to make sure our results were accurate. We repeated this process 10 times for each experimental brick and each control brick. Wow, I did not expect the results of this experiment to go as well as they did. Our predicted density of the experimental brick was less than 2% away from the actual density of it. This means that our test negated the friction of the bearings, and our repetition of the test negated the inaccuracy of the swing of the pendulum or the inaccuracy of the ultrasonic sensor. We predict that this can be applied to the human body as long as all the factors you're measuring within your AI learning model are proportional to one another. We are currently working on AWS SageMaker to build an application that will allow you to input a large amount of data and have the AI learning model predict the missing value in the data set.